Hello, Year 12 Extension 1. Okay, in this exercise, we look at a slightly different definition of exponential growth and decay and a slightly different equation. And I would strongly encourage you to look at features of the equation and be able to identify what they represent. So let's have a look at the definition. In these cases, the rate of change of a quantity is proportional to the difference. So previously you saw that the rate of change, say dq dt, was proportional, k, times the quantity itself at any particular time. But now the definition includes situations where the rate of change is really dependent on some other concept, for example, the environment. Maybe best to think about a cup of coffee or tea cooling. It will only cool to the temperature of the room, and so really its rate of change is affected by the room temperature. So mathematically the equation becomes dq dt is proportional to a quantity or temperature minus some other fixed temperature. If you have a look at that equation and compare it, it's pretty easy to see that yes, difference is being denoted with a subtraction sign, the size of the quantity at a time, and d being a constant. So we know that as the differential equation, just as we knew this one over here as the differential equation. And over here we had that solution to that could be that q is q naught e to the kt, and we showed that and used that, found the values of q naught, found the value of k, and answered questions on real life situations. Just like that, we're going to do the same. We're going to be given a solution to this differential equation. So something like this is usually given. Let's take a close look at that, where q is, like q has been previously, it's the amount, and this is the equation that you will use to calculate. So if we're talking about the temperature of a cup of tea, it would be T here, the temperature, is equal to, now remember D was this constant. So it now becomes Q is equal to D plus AE to the KT, where A is the value of Q minus D at time 0. This is really important. A is the value of Q minus D. So previously in our solution to our differential equation, we had a Q naught. That slightly changes now. That's being referred to as A, and it's Q minus D. And again, I encourage you to take time to look at this equation and note and just what it looks like in terms of, well, we're going to start with this constant value. We're now adding on this exponential expression. The reason I tell you to be really comfortable and familiar with this equation is because we've noticed that questions in the more recent HSC Extension 1 exams have actually required you to write this yourself. There are, of course, some questions where this solution is given, but increasingly we see the questions where maybe even this general format is given, and you have to know by the information that's given where the constant, they'll describe the constant to you. So in an example about how a cup of tea is cooling, the constant is going to be the room temperature. You would have to know yourself that that value needs to be placed in this position in the solution to the differential equation. A is always the value of Q minus D at time 0. And again, knowing these facts makes it much easier if you get a question where you're actually required to write out the general solution. So while you won't be asked to derive this, you may be required, as you'll see in an example in the notes, you will be required to actually fill in relevant spots in this so that you come up with a solution. So I've said there, while you're not required to derive the solution, please learn its basic form. Learn these connections between A, Q and D sitting here, and just the general format. So once you're familiar with that, there will be 3 common types of questions. One, where you'll be asked to show that this given equation satisfies the differential equation. Now, you did that. You did a similar thing back at the advanced chapter on exponential growth and decay. So you will see a couple of little different sorts of techniques that you can adopt in a solution to that sort of question. You'll be required to form the solution, like I've talked about that one, and that's probably a little bit different where you're actually forming the solution. And 3, find the values of K, A, etc., which will be the process to get those will be very similar to what you did previously. Understanding the graphs is also very helpful. It's always good to be familiar with the graphs, and I've just put the 4 of those in there. I'm going to stop this video now and do the example set.